This lesson looks at a special type of factoring called the difference of squares. Before we actually look at this, I want to review the product of two binomials and specifically how to expand it with the FOIL process. So let's look at a plus b, a minus b. In FOIL, we take the first terms, which is a times a, the outsides, which is negative ab, the insides, a times b, and then the last, negative b squared. Now normally this becomes a trinomial. We combine together these middle two terms, which are like terms. However, you notice something special happens with this one. These two terms in the middle cancel themselves out, and we're left with just a squared minus b squared. Very unique. In fact, we have a name for it. It's called the difference of squares. You'll want to memorize the difference of squares. Anytime you see a squared minus b squared, we'll factor it as a plus b, a minus b. So let's practice with several of these difference of squares. The first thing you'll notice is that all four of these examples are minus. That's required with difference of squares. We have no formula for the sum of squares. Second thing you want to notice is that for each one of these, we're going to have to pick out exactly what a and b are. The a represents the very first term that's being squared. So look at the first example, x squared minus 36. Think to yourself, what was squared to give x squared? In that case, a must have been x. To get the b, you think about what was squared to give you the 36. That must have been a 6. In order to write it out then, what I'll do is just write a plus b, a minus b. Or the factorization is x plus 6, x minus 6. No work to show at all. In the next one, think about how they got 4x squared. They must have squared something. In this case, they must have squared 2x. Same thing for the 25. B is going to be the number they squared to get that 25. It's 5. So the factorization is a plus b, a minus b. For the next one, we have the same a values previously. We know that a is going to be 2x, but then b has a letter in it. Something was squared to produce 16y squared. That was 4y. So our factorization is a plus b, or 2x plus 4y, times 2x minus 4y. In this final one, you see a variable only in the second part, but it doesn't make a difference. It's still going to be the first thing is the a squared and the second thing is the b squared. Well, here I know 8 gave the 64, and there must have been a y to be squared in the second part. This turns out to be a plus b, a minus b. Sometimes you won't actually recognize the difference of squares right away. Like if you think about it in this first example, 2 is not a perfect square, and neither is 50. However, if you factor out the greatest common factor first, some things will appear. So like here, I know that there's a 2 in common. When you factor out a 2, we get 2 times x squared minus 25. This new thing here is a difference of squares. In fact, it's an a equal to x and b equal to 5. We can continue to factor, just leaving that 2 to carry along, as a plus b, a minus b. Again, that 2 kind of carries through the whole time, but the complete factorization will have the 2 and the difference of squares in it. In the next one, currently there's no perfect squares. In fact, there's a cube there. But there is something in common. There's at least a 2, they're both even, and a y in common. So I'm going to factor out a 2 and a y, which leaves 9y squared minus 4. This new part here is a difference of squares. It's a 3y and a 2. So this 2y will just carry on down, and we'll do a plus b, a minus b. In the last one, this is kind of unique. In the last one, these are actually both something was squared. A was x squared, and b was 4. So when we do the difference of squares, a plus b, a minus b, it looks like this. The reason why this is a special problem is because part of this now, specifically that second part, is actually another difference of squares. This first one here is a sum, so I can't do anything with it. But the second one itself turned into a difference of squares, where the new value of a was x and b was 2. So although this is factored, it's not factored completely. We need to go one more step. I'm going to leave the first part alone, just because it's a sum, can't do anything with it. But then this second part, I'll do a plus b, a minus b again. X plus 2, x minus 2. That whole thing there is the complete factorization. One of the things we'll be able to do with the difference of squares is to solve equations. Now, it doesn't look like it, but both of these equations, if you set them equal to 0, will have a difference of squares in them. So like the first one, let me subtract 25 from both sides. And then complete this as a difference of squares. This is an a plus b, a minus b. We've learned before that this is the zero product property. I can set each one of these equal to 0 and solve. Either x plus 5 equals 0 or x minus 5 equals 0. We get two solutions from this, negative 5 and positive 5. Same thing's true in this next one. If you subtract the 25 from both sides to begin with, we have a difference of squares. 3x plus 5 times 3x minus 5. The zero product property says one of these things must be 0. Either the 3x plus 5 or the 3x minus 5. By solving these little equations, we get x equals negative 5/3 or x equals positive 5/3. Let's do two more equations that are a little bit more complex. Same thing is true on this next one. I'm going to move the 20 to the left-hand side. But now, just like some previous examples, it doesn't look like a difference of squares. I'm going to have to factor a 5 out first. You'll notice then that this y squared minus 4 that we just created is now a difference of squares. I'm going to carry the 5 down through and do a plus b, a minus b. Now we have three things that we could potentially set equal to 0. But remember, the number 5 will never equal 0. So I'm not even going to consider that. But we do have the y plus 2 could equal 0, or the y minus 2 could equal 0. This has two solutions, y equal to negative 2 and y is equal to positive 2. All right, one last example. In this one, once again, doesn't look like a difference of squares, but there's a common factor. There's an x. So I'm going to take the x outside and factor. The remaining part needs to be factored again as a difference of squares. I'm going to carry that x down through and do an a plus b, a minus b. One of these three factors must be equal to 0. Either the first x is 0, or the x plus 3 equals 0, or the x minus 3 equals 0. So three different solutions. I have 0, negative 3, and positive 3. The key thing is, on all of these equations, we want to get a 0 on one side and look to see, first of all, if there's a greatest common factor that can be removed. If so, it opens up that potential for a difference of squares.